In this module, we are going to continue with permutations and combinations, but this time we are going to potentially allow replacement in some of the examples. That means we choose one object, but then we can choose it again, and that's what we are going to look at in this example. Part of the things that I want to look at in this module is how we can think of different permutation problems in different ways to come up with the answer. First, let's look at what we're looking at. So suppose we want to select three numbers from 1, 2, 3, 4. Now, if we are not allowed to perform replacement, that means once we select a number, we don't put it back again where we can select it again, then the choices that we can have are we can either have the set 1 to 3 or 1 to 4 or 1 3 4 or 2 3 4, and the total number of ways that we can do this is going to be C of 4 comma 3. And if you do the math from the previous module, you will see that there are only 4 ways we can do this. Another way of thinking of this is selecting 3 is same as dropping 1, and there are exactly 4 ways we can drop one element out of 1 2 3 4. However, if we allow replacement, that means we select an item but we put it back also, and so we might be able to select it again. In that case, we have a lot of choices. So 1 to 3, 1 to 4, 1 3 4, and 2 3 4, those are the choices that we had. We still have them. But we also have the choice 1 1 2. Note that when we said the order doesn't matter in terms of what we are selecting, 1 1 2 is same as 1 2 1. However, it's not the same as 1 to 3, it's not the same as 1 to 4, and so on and so forth. So these two are same. 1 1 2 is same as 1 2 1. Order does not matter. But this was not something that we could do without replacement, because without replacement we couldn't select one more than once. And then we have these other choices, and there are a lot more choices that go on like this. Now let's think about permutation and combination with replacement. So here in permutation, the bins are numbered. So what we put in the first bin, what we put in the second bin, what we put in the third bin is going to be going to matter, and therefore these combinations are all going to be different. In combination, we said the order doesn't matter, so we previously thought of it as a set. Now we can't think of it as a set, because in a set we were not allowed to have the same element more than once. But what we're going to think of is, let's look at these combinations. So here I have three objects that look like this, and here also have three objects that look like the same, and I have one object that is like this and one object that is like this. So essentially, in a combination, if I reorder things, then I get something that is the same thing as far as counting is concerned. So in terms of combinations, this set, let me mark it one more time. This combination is same as this combination, because essentially you could think of it as, let's say we were looking at numbers, then we always write all the numbers that we have in a sorted manner. So if some number is repeated, we write that many times, but we write them in, say, increasing order. Now is it the same? And in case of combination, that is going to be the same. So we are basically looking at the set of elements that I have. So how many ones I have, how many twos I have, how many threes I have, That's what is going to decide what my set is. So it's going to be here. I have how many of the blue colored balls I have, how many of the purple colored balls I have, how many of the red colored balls I have. That's going to matter, but the way I organize them is not going to matter. On the other hand, in permutations, the way I organize them is going to matter. So here I have the same set of balls. These three are identical to these three, and this one is identical to this one. But they're now organized in a different way, and therefore these are two different permutations that we are going to have. Let's see if we can solve this using the same thing that we did before. So let's review what we did when we were not allowed to do replacement. And what I'm going to show here is that what we did before doesn't work. The reason is as follows. Let's look at one of the combinations of 1 to 3. If I had the combination 1 to 3, how many permutations can I get? I can get quite a few permutations out of this. These are the permutations that I'm going to get out of 1 to 3. And we can see that this number is 3 factorial because I have 3 elements and I have to arrange all 3 of them. On the other hand, if I was looking at the combination 1, 1, 1, then there is only one permutation that we can get, namely 1, 1, 1. If we try to create more permutations like this, they're not going to be different because all 3 elements that I have are basically identical. In other words, which combination we choose is affecting how many permutations we can do. And that was not allowed in the product rule. In the product rule, what we said was you do the first task. In this case, the first task was selecting the combination. And then you do the second task. But it's important that when you do the second task, the number of ways in which you can do that must remain the same. In this case, it is not the same. If I choose the combination 1 to 3, I can do 6 permutations. If I had the combination 1, 1, 1, I could just do 1 permutation. And that's why we are not going to be able to apply the product rule to solve this problem. Once again, we have reached the check before you go ahead slide. I want to make sure you have understood why we cannot use PNR and CNR when repetition is allowed. And in particular, how is it that the lack of repetition is assumed in the formula for PNR and QNR? Sorry, PNR and CNR. Next, we'll look at how to relate this problem to another problem, and one of the key ideas of this set of modules is how do you relate different problems to each other so that you can apply different counting techniques from one domain to another.